So the last thing we have to do before we leave this section is return briefly to the octet rule and go through some exceptions to that rule. And there are actually several exceptions that we encounter. The first is any case where we have an odd number of valence electrons total. So if we have an odd number of valence electrons, we certainly can't satisfy the octet rule for all of the atoms. And so what do we do in those cases? The second is any case where we have less than 8 valence electrons. We've gone through some of those examples with hydrogen, lithium, or beryllium. There is one other example that we need to mention for cases with less than 8 valence electrons. And then finally, there are several examples of cases where atoms can have more than 8 valence electrons. And so we need to discuss that briefly. So let's start with odd number of electrons. Let's just take a nitric oxide. It's a common atmospheric gas here as an example. Now, nitrogen has 5 valence electrons, oxygen has 6, so in total we only have 11, which is an odd number. So there's no way that I can draw a Lewis structure that satisfies the octet rule for both atoms. What I can do is draw two different Lewis structures here, one where the unpaired electron is on nitrogen and one where the unpaired electron is on oxygen. And we have to then decide which of those two we would prefer. Well, whenever we have the opportunity to draw multiple Lewis structures with odd number of valence electrons, we want to draw the Lewis structure that minimizes the formal charge. So we'll choose the structure here that has the fewest or smallest, in the case that we can't limit it entirely, formal charges. If we look at the structure on the right above and do the formal charge real quickly, nitrogen, 5 valence electrons minus 2 bonds, minus 4 unshared, that's -1. Whereas oxygen, 6 valence electrons minus 2 bonds, minus 3, that's +1. But on the structure on the left, nitrogen, 5 valence electrons minus 2 bonds, minus 3, in this case, nitrogen has no formal charge, and the same thing we'll find if we work through the formal charge for oxygen. It is also 0, so we would prefer the structure on the left here when drawing the Lewis structure and depicting how the atoms are bonded in nitric oxide. We extend this analogy to any other case where we might have an odd number of total valence electrons. The second case is examples where we have less than 8 valence electrons. And we'd already gone through hydrogen, lithium, and beryllium, those cases. There's one other element that we should note that actually prefers to have less than 8 valence electrons. And that's boron. And we can illustrate this by going through the example of BF3. So if we draw BF3 by putting boron in the middle and then the fluorines on the outside, we initially come out with this structure shown here. And where all of the fluorines are satisfied, they all have a full octet, but boron only has 6 electrons. If we go to satisfy the octet by sharing an electron pair from fluorine, what we notice is that regardless of which fluorine we share from, we end up inducing some formal charges. So the fluorine that shares its lone pair gets a +1 charge, and boron always gets a -1 charge in all cases. However, if we look back at the original structure where boron wasn't satisfied or didn't have a full octet, if we do the formal charges in that case, they're all 0. So it turns out that boron actually prefers just 6 valence electrons. So we would actually choose to draw the structure on the left as the normal Lewis structure for BF3. Because boron in all cases prefers to have only 6 valence electrons, if we're able to draw a structure where it has only that many. So then the last example, of which there are more than one, is cases where we have more than 8 valence electrons. This is breaking the octet rule. And we can actually break the octet rule in a number of cases, but there is one limitation. We must be in row 3 or above in order to have more than 8 valence electrons. If the elemental is only in row 2, is only in row 1 or 2, we can't have more than 8 valence electrons. That would violate its ability to bond. But we can break that octet rule for elements that are in row 3 or greater. So let's work through a few examples of this and illustrate it. The first is the sulfate anion, SO4 2-. And we'll treat this just like we would normally for drawing a Lewis structure. So first, we'll note that sulfur has 6 valence electrons. Oxygen also has 6, but there are 4 of them, so that's 24. We've got a 2- charge, so that's an additional 2. And we sum all that together and we have 32 valence electrons total. Sulfur goes in the middle since it's lower down on the periodic table and it has the same valence as oxygen. So initially sulfur in the middle, oxygen on all the sides. That will remove 8 of my electrons. Now I'm back down to 24 in this case, and then I work my way around filling out the outer atoms. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, and let's see if I've made an error here somewhere. 30, 32, we use 8 initially, and then that would leave us 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oops, I simply miscounted. So I used all of my electrons. I have none left. And you might look at that structure and wonder why I would suggest this is breaking the octet rule, because sulfur has 8 electrons around it. It's satisfied. Oxygen, all of them have 8 electrons around them. They should be satisfied. So this should be a good structure for SO4 2-. But in reality, this isn't actually the structure that we draw for SO4 2-, because if we look at the formal charges, we'll note that each oxygen has a -1 formal charge and sulfur has a +2 charge. If we take a lone pair from 2 of the oxygens and bring them in to share to make double bonds, that would get us to this structure shown here, where sulfur has a double bond to oxygen, or to 2 of the oxygens. And our structure looks something more like this. The other 2 oxygens still have just a single bond. And the formal charge on these 2 single bonded oxygens is still -1. But the formal charge for this for the other oxygens is now 0, and for sulfur is now 0. So I've limited the formal charges. Now, I've broken the octet rule. Sulfur now has 8, 10, 12 electrons around it. But I've minimized the amount of formal charge in the compound. And that actually leads us to a case where we are allowed to break the octet rule if it minimizes the formal charges in the compound, providing that the element that we break the octet rule for is in row 3 or greater. So we prefer the structure that has the smallest formal charges. In this case, we prefer the structure on the left over the structure on the right. So with that in mind, we can look at just a couple other examples. PF5, this is a slightly different case here, where it's not that we are all satisfied, but then we pair something up to minimize formal charges, as we did in SO4 2- here. PF5, well, phosphorus goes in the middle. We have a total of 5 plus 5 times 7. So we have 40 valence electrons. Phosphorus goes in the middle, and then if we arrange all of the fluorines around it, what we see is that we have 5 fluorines, so we make 5 bonds. And right there, we've broken the octet rule for phosphorus. That's actually okay because it's in row 3, and so having 10 electrons around it is okay. That uses up 10 electrons, and then we put the remaining 30 around the fluorines. And use them all up, and notice that our formal charges are all 0. And this is okay for this example. If we tried to connect it in somewhere where we only had 4 fluorines around phosphorus and then connected that extra fluorine to one of the other fluorines, we would end up with a bunch of formal charges that we don't want. So that's sort of how we would do a case where now we can have more than 4 atoms bonded to the central atom. There's one more case that we should look at here, and that is the last case here of ICl4-. So iodine has 7 valence electrons. Chlorine also has 7, but I've got 4 of them, so that's 28 valence electrons, and I have a -1 charge, so that's an additional 1. And what we come out with then for total is we end up with 36 valence electrons. Iodine and chlorine both have the same valence. They're monovalent. They have only a valence of 1. But iodine is lower in the periodic table, so I put it in the middle. So iodine goes in the middle. The 4 chlorines go on each of the 4 faces. And that uses up, of my 36, that uses up 8. So I'm back to 28. Now I put electrons around the outside, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And I'm left with 4 electrons left over, but I've already satisfied the octet for the outer atoms. So those remaining 4 electrons I put on the central atom, and they go as simply lone pairs. I could place around iodine. Now that breaks the octet rule for iodine. It now has 4 bonds, so that's 8 electrons, and then 2 more lone pairs. So it has 12 electrons around it. But that's okay because it's in a row greater than row 3 or greater. And if I calculate the formal charges on all of this, I will find that the chlorines are all 0, and iodine has a -1 charge, which matches with the overall charge on the compound. So that's how we would go about dealing with these exceptions to the octet rule and how we should approach in each case. If we're given a compound where one of the elements is in row 3 or greater, we'll first just draw the normal Lewis structure, and then we can adjust, add extra double or triple bonds even if we need to, in an attempt to lower the minimize the formal charge in the compound.